My YouTube channel is James Cook Math. Yeah. So, James Cook Math. If you can't find it, come see me in the math department. I'm pretty easy to find. All right, so I will start as soon as I get some markers here. Let me begin with a word of prayer. So, dear Father, we thank you for this day. Again, I thank you for these students, and so ask you to bless our work, help us to understand a little bit more about your creation today, Lord. In your name I pray, Lord Jesus. Amen. All right, so let us talk about the dot product. So here's the definition. If A is a vector, so we can write that A1, A2, A3. Now the notation Dr. Skambordis has probably been using is this, like A1 I hat plus A2 J hat plus A3 K hat. I personally don't like that notation. If you're in my class, we use this A1 X hat plus A2 Y hat plus A3 Z hat. The reason I use X hat, Y hat, Z hat, because those are the unit vectors in the X and the Y and the Z direction respectively. And this is a notation that's more common in physics and engineering, higher level anyway. So that's a vector, and if also B is a vector, so I'll just put it up here, B1, B2, B3, all right, then A dot B is by definition A1, B1 plus A2, B2 plus A3, B3. So this is the dot product of A and B, or you could also call it the scalar product of A and B. So I don't have any idea how you guys top hat in here, nor do I care to learn. So we're going to do this thing called attendance on a piece of paper. And so what I would love for you to do, for the sake of Dr. Skambordis, knowing who is here, would be to print your name on. I don't want a signature. I would like a print of your name. And that would be the best way to do it, right? So if you can print your name, that'd be awesome. And then pass it on. Okay, so that's the dot product. And properties of the dot product, let me put up here. It's really nice. A dot B is equal to B dot A. So it's like a commutative product. If you have A dot B plus C, if you got two vectors, it's A dot B plus A dot C. So it distributes across addition like that. That's super nice. What else does it do? If you've got a constant, if I have like A dot product with a constant times B, you get a constant times A dot B. So you can pull constants out of the dot product. Also very nice. All right. So, great. What else could we do with the dot product? What happens if we take the dot product of A with A? We got what? A1 squared plus A2 squared plus A3 squared, right? Think about taking the dot product with a vector with itself. You got A1, A1, A2, A2, A3, B3, A3. So in other words, I give a formula here that the length of A is equal to the square root of A dot A. Did you guys have another symbol for the length of A? Usually our custom in physics is if we're talking about a vector and we drop the vector symbol, like so, that is notation for the magnitude or length of the vector, right? So if we take the square root of the dot product of a vector with itself, it gives us the length of the vector. This is very nice. All right. Have you guys talked about unit vectors in here? Slightly? All right. So what's the significance of the magnitude? Like just, this is kind of a, I'm chasing a rabbit here for a second, but I've only got so much board space. So any vector, almost any vector, can be written as a times a hat, right? A times a hat. Now that's not always true. What's this make a hat equal to? One over a times a, right? So this right here is a unit vector in a direction. Now you might be wondering, wait a minute, physically what are you talking about? Dr. Skambordis has been talking about like position vectors, velocity vectors, acceleration vectors, right? And I think from what I saw in the notes that one of you showed me, he's also been doing some stuff with like constant acceleration, right? So that's sort of one-dimensional. You don't really need vectors for the one-dimensional context, right? Plus or minus will give you up or down or left or right, give you a sense of direction. But for vectors in 2 or 3 dimensions, we need vectors to capture the direction. So this right here is the unit vector, and any vector can be written as a magnitude times its unit vector. I keep saying any vector, but that's a lie. When is it not true? What's that?
What was that again?
Which vector can I not write as a magnitude times the direction? Which vector has an undefined direction?
The zero vector?
The zero vector, right. Zero to vector, you're going to have a lot of trouble doing a hat for a equals to 0, right? Because you have to divide by the length of the zero vector. Hey, the length of the zero to vector is defined. It's what? Not a trick question. The length of the zero vector, you coming in?
Yeah.
Okay. 4368?
Yeah.
Okay. Yeah, Dr. Skambordis is sick. Stuck with me today. So, so yeah, the length of the zero vector is defined. It's just 0, but its direction's not defined. Okay, so but as long as a is not equal to 0, we can write the vector as a magnitude times the direction. All right. Let me take a step back here and give you an example of that. Suppose I have vector a is 1, 2, minus 2. All right. Let's calculate a dot a. What's a dot a here? One squared plus 2 squared plus minus 2 squared, also known as 1 plus 4 plus 4, more commonly known as 9. So what's the magnitude of a then? Yeah, the magnitude of a is 3, so the square root of a dot a, which is square root of 9, length is 3. So I can rewrite a as equal to 3 times the vector 1, 2, minus 2 divided by 3. The vector I just wrote in parentheses, which of course I could simplify if I wanted to, right? I could rewrite this as 3 times the vector 1/3, 2/3, minus 2/3, right? That is a unit vector. Do you believe me? Let's check. Is this a unit vector? I hope so. Try it out. The square root of 1/3 plus 2/3 squared plus minus 2/3 squared. What do you got? That's 1/9, 4/9, 4/9, also known as the square root of 9/9, also known as 1. All right. This is not an accident. You can prove, generally speaking, that the unit vector constructed as such has length 1. It's a simple calculation to do, right? I'd encourage you to try it. Prove to yourself that a hat necessarily has length 1, right? Do you guys know how to do that? No one cares?
Take the square root of
Oh. Yeah, okay, let's try it out. So the length of a hat, right, is the length of, I think what you said was okay, 1 over a times a vector, right? But what is a property of vector length? Do you guys remember? If we take a vector and calculate its length, one of the properties of vector length, I mean, I guess we'll do the square root thing. So this is the square root of 1 over a times a vector dotted with 1 over a times a vector, right? That was a formula we found for vector length a second ago. So what happens there? You got 1 over a, those are just numbers. So this is 1 over a squared, and then you've got a dot a, which is what? Well, it was 9 for my example, but this is, we've left that example behind. You're fine. This is a squared times 1 over a squared, also known as 1. Square root of 1? 1. This calculation holds for any non-zero vector. So if you want to create a unit vector in the direction of a vector, you simply rescale by the reciprocal of its length, right? What if I wanted to find a vector length 10 in the 1, 2, minus 2 direction? What would that be? I want a vector of length 10. So question. Find vector length 10 in, a direction, where I'm talking about the a from example 1. Can you tell me the answer to that?
Multiply 10 times the unit vector in that direction.
So you're like 10a hat, that's it. Oh, my Q&A is unfortunate. Let me give this vector a name. I'm going to call it Pac-Man. It's a Pac-Man, so you got to put a vector. If it's a vector, I got to put a vector on it. So Pac-Man as a vector is 10a hat. Now, in particular, I'm talking about, let's see here, 10 times 1/3, 2/3, minus 2/3, right? So that vector right there is the answer to the question. That would have a length. If you take a unit vector and you multiply it by a number, the length of the resulting vector is simply that number. That's it. Unless the number is negative, in which case it's the absolute value of the number, right? If I put minus 10 a hat, right? That would also be a vector of length 10, but it wouldn't be in the a direction, right? It would be in the opposite direction to a. All right. So there's just chased a rabbit on the unit vector here for a second, but if you guys didn't know about that before, I'm going to end up using it at some point in the rest of the lecture, so let me just get it out of the way, because I don't know what you guys know. Because Dr. Skimbortis didn't plan to get sick, he just got sick, right? So, and the secretary told me that you guys were on schedule, but that doesn't mean anything to me. So, all right, so let me put this away. Let's get back to the dot product, now that we know a little bit about magnitudes and all. Let me get the juice. So again, I am recording this lecture, so if you miss something, you can look at it on the YouTube later if you want. And if you also want to see, how horrible the teaching is in the other section of Physics 231, you're welcome to look at my lectures. What's that? James Cook Math. James Cook. No E. What's that?
Show them the website.
Oh, the website. This is true. My website, good point, is www.supermath.info because it's cheaper. So, all right. Anyway, if you look in there, you'll find links to my YouTube channel and tons of other things. All right, so I want to talk more about this dot product. So we figured out already that the dot product of a vector with itself gives us the length squared. What else does it do for us? It's helpful to look at a triangle. So let's see if I can do this right. It's anybody's guess. Suppose this is A, right, and B, So there's A, there's B. I'll put C. I guess I'm going to put C like this. If I do that, can you guys tell me in terms of vector addition how A and B and C are related?
A plus C equals B.
I've got an A plus C equals B. Very good. Tip to tail, right? Now, let us solve. Let's put some things in here. This angle we're going to call theta, right? So what do you know once I draw a theta there? The length, the lengths of the legs here are what, respectively, like A, B, right, and C over here. So what do we know? We know that A squared plus B squared minus 2AB cosine theta is equal to what? It's equal to C squared. What is this? This is the law of cosines. Now this is more familiar to you guys. If we put theta equal to 90 degrees, then you've got a right triangle. It reduces to the Pythagorean theorem, A squared plus B squared equals to C squared, right? Fine. But this is what happens for a possibly not right triangle. It's the law of cosines. All right, so this here, we can solve for C, and we get C is B minus A for my picture, right? C is B minus A. So if we want to understand the connection between the dot product and the angle between the vectors A and B, this is the thing to look at. What is C dot C then? Well, C squared, right? C squared is C dot C. But that's also equal to B minus A dotted with B minus A, right? But I just told you the properties of the dot product like 3 minutes ago, so you now know them, right? Once I say it, it becomes committed to your memory. Them's the rules of lecture. So that's a joke. Let's see here. B dot B minus B dot A minus A dot B plus A dot A. But what's that equal to? We can simplify this. What's B dot B? B dot B? It'd be B squared. And A dot A, it'd be A squared, right? So I've got B squared minus 2 A dot B plus A squared. But notice that this, right, has to be equal to this, because they're both equal to C squared, right? So what does this tell us? Thus, A dot B, apparently, is equal to A, B, cosine theta, right? If I cancel out the minus 2. Do you guys see that? Just like an algebra step I didn't write down. So you cancel the A squared, cancel the B squared, divide by minus 2, we get A dot B is AB cosine theta. So let me complete the thought up here. The dot product is also given by AB cosine theta. So if you want to calculate the dot product between a pair of vectors, if we know the magnitudes of the vectors and we know the angle between them, we can calculate the dot product. But you should understand that this right here, this is essentially the law of cosines. Right? This is essentially the law of cosines approximately. I mean, that's not, I should put some quotes on here. It's not quite the law of cosines, but it's essentially a corollary to the law of cosines from the calculation I just did, right? As such, it is a non-trivial formula. It reveals things geometrically that are otherwise hidden. So you can use this formula to understand things about three-dimensional geometry, which are otherwise a little bit difficult to figure out. Let me show you. So standard example I always do is to calculate the angle between some vectors. So we'll do that. Well, let me just give you like a little theorem. Suppose you want to calculate the angle between vector A and vector B. How would you do it? So like theorem, if A and B are not equal to 0, then the angle between A and B, right, is equal to the inverse cosine of A dot B divided by AB. To find that theorem, all you do is take the formula we just derived, divide by AB, and take the inverse cosine of both sides. All right? So let's put this theorem into practice. Example, I guess 3, I don't know. So suppose you've got a cube, like so, all right? And we'll say that it's like, you know, this point here would be like 1, 0, 0. This point down here would be like 1, 1, 0. This guy up here, 0, 0, 1. This point out here, 1, 1, 1. You guys with me? So I'm basing the cube such that it's like back corner here is at the origin. You got me? Now I'm going to ask a question, which is what's the angle between two vectors? The vectors we're going to consider are the vector that comes from the origin up to this point, which I'm going to call that A, and another vector back here that goes up to that point right there. I'm going to call that vector B. My question for you guys is, what is the angle between A and B? Anybody care to guess?
$45.
45. Thank you. Very good. Hoping for that. Incorrect, but that's what I wanted. So A is the vector. Somebody always guesses 45. Like it's a law. You're about the 7th person in the 7 times I've done this before. I think about 7. I really am not keeping track. But so the vector A, it goes from the origin out to 1, 1, 1, right? So it's the 1, 1, 1 vector. The vector B goes from the origin up to 0, 0, 1. So that's the 0, 0, 1 vector, also known as k hat for you guys, or z hat for my students. Now, what's the magnitude of A? Square root of 3. What's the magnitude of B? B is a what? Right. B is 1. B is, in fact, a unit vector. It is the unit vector in the z direction. So what's the angle between A and B? The angle between A and B, which I've called theta, right, would be the inverse cosine of A dot B over AB. Now, I forgot to calculate A dot B. What is that? What happens when we take the dot product of A and B? 1 times 0 plus 1 times 0 plus 1 times 1. So the dot product of A and B is 1. And AB is square root of 3. The inverse cosine of 1 over square root of 3 is about 54.73 degrees. Right. So your intuition about angles between three-dimensional vectors can be deceiving. This is why vectors are important, because they allow us to calculate analytically angles between things we can't draw good pictures for. That's a little bit unfair here. You could draw a better picture, right? Why is it not 45 degrees? Do you guys understand why that is? I mean, 45 degrees is a reasonable guess. Somebody always guesses it. Check it out. If we were to take the plane which these two vectors lie in, this plane here, right? And if I was to take that plane and like lay it flat, like this, so these points would be what? The origin. This point down here would be like 1, 1, 0. This point up here is my 1, 1, 1. This is my z hat point, 0, 0, 1. Right? And so in this picture, my B vector is here, and my A vector is over here. Right? I've not drawn this to scale, but you tell me, what's the length of the rectangle? It's a rectangle, it's not a square, is my point. What is the length? So like in green, the length of B is 1, right? How far is it from here to here? Square root of 2, right? And this guy, square root of 3. And that's why the angle, theta, is inverse cosine of 1 over square root of 3. Because you can reduce it to right triangle trigonometry if you have the vision to see it as such. But if you don't have the vision to see it as such, you can still calculate dot products with vectors easily, right? Let me show you another example of this business here. Feel free to jump in with questions if you got them, guys. All right. Let us look at the vector. Let's look at B equals to 2, I'll tell you what, 3, 0, minus 4. My question is, find angle between B and the positive x, y, and z coordinate axes. So how should we do this? I mean, I can try to draw you a picture of it, and this picture is totally schematic. I don't even care where B goes. I'm just drawing you what I mean by these angles. So we're asking, what's the angle like this, which I guess is usually called alpha? What's the angle like this, which we usually probably call beta? And what's the angle like this, which is probably called gamma? I believe these are called Euler angles. Right, so those are, it's the angle between the vector B and what? Yeah. Yeah, we just use the unit vectors. So let's get to it, right? Like alpha. Well, let's just write down the formula here first of all. So like B dot 1, 0, 0, right, is equal to the magnitude of B times the length of 1, 0, 0, which is 1, times the cosine of, well, alpha. So that tells me that, well, what is the length of B, though, is the question. I guess I should probably figure that out. You guys tell me. I heard a 5. I'll accept it. So what's B dot 1, 0, 0 is what? We got 3 is equal to 5 times the cosine of alpha. So alpha apparently is inverse cosine of 3/5, which you could calculate if you want. I don't really feel like it. I didn't get paid enough for today, so. Sorry, I'm an idiot. On the other hand, if we take, B dot 0, 1, 0, that's going to be B times the cosine of what? So this is in the y direction, right? So this is going to measure the angle from the positive y-axis to my vector. And I called it beta. So this tells me that, let's see, the dot, well, that's 0, right? 0 is equal to 5 times the cosine of beta. I don't need a calculator for that. I can tell you that beta is equal to what? Is 5 0? No. So if we have 5 times something is 0, it means that cosine of something has to be 0. So this makes beta equal to what? Aren't you guys engineers? What? 90. Okay, yeah. So yeah, talk a little smack, shake you from your slumber. Let's see here. Sorry, I'll behave. B dot, that's not true. B dot, I can only misbehave. Where am I? Oh, 0, 0, 1. So this should calculate the angle between B and the z-axis. b cosine gamma, right? But what's the dot product of 0, 0, 1 and b? We get 0, 0 plus 0 minus 4. So we get minus 4 is equal to 5 times the cosine of the angle I don't know, gamma. Therefore, gamma is equal to inverse cosine of minus 4 over 5. I guess I'd feel better if I find the numbers. It's kind of bothering me. It is a physics class after all. We should give numbers, right? I mean, I can't speak for Dr. Skambordis for sure, but I personally am annoyed when students leave answers like this on a test. Like if it's physics, I want a decimal, you know? Of course, I also don't want radians. I like degrees. Because, yeah, where's the 5 coming from? Well, you guys told me 5. If that's wrong, that's on you guys. Let us calculate that. So b is the square root of b dot b, which is what? The square root of 3 squared plus 0 squared plus minus 4 squared. Eventually, you stop caring about those minuses, right? So that's the square root of 25, also known as 5. Oh, good. You guys are right. That's a relief. So, whew, man, I'll tell you what. 53.13 degrees, apparently. And this one, inverse cosine minus 4 divided by 5. Got a 143.13 degrees, like that. Yeah. I'm curious, what happens if does anything happen if we look at cosine squared alpha plus cosine squared beta plus cosine squared gamma? Does anything interesting happen there? What is that? We get what? We've got like a 3/5 quantity squared. So 9 over 25 plus 0 plus 4/5 squared gives us 16/25. Hey, look at that. That's a what? I learned that from Dr. Sprano. Let's see here. 25. Do you guys have Dr. Sprano for anything? Some people do. You know what I'm talking about. I like Dr. Sprano. Anyway, it's equal to 1. That is not an accident of this example. This is a general truth about Euler angles. If you take the sum of cosine squared plus cosine alpha squared plus cosine beta squared plus cosine gamma squared, where they're the Euler angles, it's always the case that the sum of the cosines is equal to 1. What this means technically is that if you calculate 2 of them, you can use this formula to find the third one. So, have you guys talked about like standard angle of a vector in 2 dimensions yet? I see some no. All right, let's talk about that. So the competitor, well, before I erase this, any questions about this? It's a pretty standard question in this course, to find the angle between a vector and like one of the coordinate axes, yeah?
What would be the difference if you got positive or negative angles when you as a result of calculating?
If you get a negative angle, you need to throw your calculator out. Because inverse cosine is from 0 to 180, so it's impossible. And that actually is a good question, because it speaks to the question of how do we define the angle between 2 vectors? And the answer is, that is how. That defines actually the angle between 2 vectors in 3 dimensions. Actually, there's nothing particularly 3-dimensional about this. I could easily do this. That's still true. This is actually not 3-dimensional coordinate geometry. This is n-dimensional coordinate geometry, truth be told. And we'd still define the angle in that way, even though don't ask me to draw a picture of 5-dimensional vectors. I can still calculate the angle between them, right? Yeah. One other thing I should mention before I forget. If a dot b is 0, we have a special name for that. What's that? A dot b equal to 0 if and only if A is perpendicular to B. So this is also sometimes, this is got perpendicular, Or if you want to impress Dr. Scambortis, you can call it orthogonal. That will make him happy. Orthogonal. I think it'll make him happy. So orthogonal is just another word for perpendicular in the abstract sense. And what's the angle between perpendicular vectors? 90, right? So 90 degrees. You might say, well, maybe it's 270. Well, we perpendicular vector, we define the angle between two vectors between 0 and 180. All right? But that's not to say that we don't consider negative angles in here. We certainly do when we think about polar coordinates, which is what I'm about to talk about. So we can write a vector as a magnitude times a direction in 3 dimensions. You can also do it in 2 dimensions. I suppose you can do it in 1 dimension, but we don't. We've kind of got our own particular list of quirky formulas for 1-dimensional stuff in here. So if you're a mathematician, it'll kind of make you go nuts a little bit. But man, come on, juice, put me down. So let's talk about 2-dimensional vectors and the issue of direction vectors there. If I'm talking about 2 dimensions, then I can write A is equal to, I might use like A1 and A2 if you like. All right, so 2-dimensional vector. If I draw a picture of that, right, like this, say, then you guys tell me, if I look here at this piece, that's what? That's A1, right? That length is A1. I mean, I could actually make that a vector. This is A1 I hat, right? And the vector like this is A2 j hat, You can write the vector as a sum of its x vector and j vector components. A1 I hat and A2 j hat. These are both vectors. It's the x part of the vector and it's the y part of the vector, themselves being vectors. As you can see, listen to me. As you can see, the tip to tail sum of the blue vector and the red vector gives me the black vector, right? Okay, great. So on the other hand, my picture is super cluttered at this point, so I want to drop the vectors for a second and just look at it as a problem of geometry. So here's A. I just mean whatchamacallit. I just want to talk about the distances is what I'm trying to get at here. I'm sorry, I've lost my words. So forgive me. So A1 and A2, the hypotenuse is A. What'd I do? Does this not make sense? See here, so that's x, that's y. Oh, you guys already know this from high school, right? But if this angle here, we define this angle theta. So theta is measured in the counterclockwise sense off the positive x-axis, right? Then theta is the so-called standard angle. Standard angle. And what are the formulas for A1 and A2 as they relate to the standard angle? Like A1 is what? What's A2 in terms of the standard angle?
A1 is A cosine theta.
Mm-hmm.
A2 is A sine theta.
A sine theta. Very good. That's it. But there's more. So check this out. A vector is equal to then A1, A2. But we can rewrite that as A cosine theta, A sine theta. And by the properties of vector scalar multiplication, we can pull A out. And then we've got A cosine theta, sine theta. Right? But we also know something from earlier in this lecture, which is the vector if it's non-zero, right? And by the way, I better assume A is not equal to 0 here, right? Otherwise, what's theta? What's the standard angle of the origin? You're like, it's 90 degrees. Well, I can't argue with you, but I say it's 13 degrees, right? We can all have an opinion. But I think generally speaking, the consensus is that the origin's angle is not defined. Which is a little bit unsettling because you use polar coordinates to calculate things that include the origin all the time. But most of these things that you're doing are integrations, and if you lose a point, it doesn't matter to the integration. Unless, of course, the function blows up there, in which case, But anyway, whatever. Not physics. So this is also equal to a hat, you see? So what is this? What happens if you divide by a? See, a hat is also equal to cosine theta sine theta in this context. So if you tell me the length and you tell me the standard angle, that uniquely specifies which vector we're talking about in the plane. Right? In 3 dimensions, this doesn't work. Right? You can't specify a vector with a length in one direction. Excuse me, a length in one angle. Right? That's not enough. It turns out you actually need 2 angles. So the Euler angles are kind of overdetermined because of that cosine squared plus cosine squared plus cosine squared equal to 1. You could actually specify a 3-dimensional vector with just 2 choices of angle. Perhaps you've thought about this before if you've looked at the world, right? Latitude and longitude. To a good approximation, the world is a sphere. I mean, technically it's an oblate spheroid. For some of you, perhaps it's flat. I don't know. I say it's a cylinder. But oftentimes in physics problems, we assume the Earth is flat as a first approximation because we don't consider the motion of the Earth around the sun or anything, or the fact that we're spinning, right? Like that kind of non-inertial motion, the accelerated frame which we're all in, we typically ignore in physics problems, right? You don't ever ask, like, okay, it's an inclined plane, but where is it with respect to, like, where's the moon right now? I need to, calculate the gravitational effect of the moon on the ball sliding on the plane. No, we don't do that, right? So we assume that it's just kind of sitting there on a flat Earth, really, and it's not moving. That's how physics problems are done. We're all flat earthers. For the sake of your problems, but you'd like it that way, because if we make the inclined plane start spinning and stuff, then no one can solve the problem. It becomes less of a Homer problem and more of a job, right? So we'd have to pay you to do it. All right, let's look at an example here. What example? Am I example 4? 5? 5, okay. Let A equal to, I don't know, minus 1, 1. Find magnitude and standard direction. So by default, theta means standard angle, but that's not written in stone in here. Sometimes theta may be given another meaning. Be careful not to assume that an angle is the standard angle if it's not said to be such. It's a good way to lose points. Okay, so anyway, what's the magnitude? A is what? Square root of 1 plus 1, which is square root of 2. So the magnitude is the square root of 2. And if I draw a picture of it, where is this thing? Right. So then, all right, so then what's the standard angle there? Do I need to get my calculator, or can you just tell me? I heard a 135. Does everybody agree with that?
Yes.
Gentleman in the front speaks for everyone. Very good. He's your leader now.
No one else.
No one else can say anything. But you guys, yeah, it's 135. That is true. Because this is 45 degrees, because you've got 1 and 1 here. So that's 45 plus the 90. 135 is, in fact, the standard angle. Yeah. Now, you might notice, by the way, that, so we have A2 is equal to A sine theta, A1 is equal to A cosine theta, right? So this tells us that A2 over A1 is what? The A's be canceling, and we get sine theta over cosine theta, also known as tangent theta. And so this is the source of much suffering, if you're not careful. So it would appear to us that theta is the inverse tangent of A2 over A1, right? And this is true sometimes. Sometimes. How about here? What's the inverse tangent of A2 over A1? Well, that's the inverse tangent of minus 1. Because 1 over minus 1 is, or minus 1 over 1. No, wait a minute. 1 over minus 1. It doesn't matter, it's all minus 1. What's the inverse tangent of minus 1? It is minus 45 degrees. And these are not equal. Not even geometrically, right? What's going on here, of course, is that we're finding the angle of this guy down here, right? Like B equals to 1 minus 1 has theta sub B equal to minus 45 degrees, right? So just as a reminder, you can only use inverse tangent directly if your vector lies in either quadrants 1 or 4. If x is negative or 0, the x component of the vector is negative or 0, you have to think through it, all right? So draw a picture to keep yourself out of trouble. All right, so when we're in 2 dimensions, we can use magnitude and direction in terms of standard angle. So we have dot product, right? So the next thing I'll talk to you guys about, well, you tell you what, I was thinking of talking about the cross product today, but I think I'm going to leave that for Dr. Skimbordas. He can talk to you about that later. The cross product is another thing we can do with 2 vectors to get a third vector, which is perpendicular to the first 2. All right. So I'm going to leave that for Dr. Skimbordas. I think what I'm going to do, in the time remains, is look a little bit at motion and how we can use dot products to formulate things involving motion. All right. So what I'm going to study is, I guess first I should tell you about the calculus of paths just a little bit. All right, so I need to erase these things. So Dr. Skimbordas has talked to you guys about position, right? Yeah? Yep. Okay. And all right, so let's see here. So if we have 3 dimensions and we've got some particle moving along some path here, all right, then at a particular point, we can look at its position, r vector, right? And at that point, we can calculate the velocity vector maybe like this, all right? What's the formula for all this? So we have r is position. Then vector v is velocity, that's dr dt, right? Now let's suppose that we're looking at, a path, a trajectory of a particle, right? And let's suppose that that particle's trajectory is not linear. And also, let's suppose that it doesn't stop. It's a non-stop, non-linear path. Non-stop, non-linear. So non-stop means that the speed, what's the speed, by the way? Speed is the magnitude of the velocity, right? So we can write the velocity as v hat. Now, in Calculus 3, you will learn that the unit tangent vector is denoted by a big T. So big T is the unit tangent vector. It's the only unit vector I don't put a hat on. In textbooks, it's bold. I don't know how to write bold on a whiteboard, you know? So that's why we put hats on things. But big T is the unit tangent vector. So that points in the direction of motion. So first of all, here's something you can easily check. T dot T is what? It's 1. Because the vector has length 1. Did you know that there's a calculus for functions? Like these sorts of, if we have a vector of functions of t, you can differentiate those component-wise. And there's also a product rule for dot products. So like the product rule for dot products, like this, if we calculate t dot t, differentiate with respect to time t prime, that ends up being t prime dot t plus t dot t prime. That's the product rule for dot products. And over here I'll use the other notation just to emphasize what's going on. d dt of 1 is equal to what? I see a 0. I'll allow it, correct? And the dot product commutes. So what this tells us is that 2t dot t prime is equal to 0, which is to say that t is perpendicular to t dt dt. T is perpendicular to its derivative. Right. So in calculus 3, we then define what's called the unit normal. N is equal to 1 over the length of t prime times dt dt. I know I'm using like prime for the one derivative and actually writing the derivative out for the other. I hope you can forgive me for this lopsided expression. You could put primes in both spots if you want, whatever. This is the unit normal. Do you guys see why it's a unit vector? Right? Manifestly n dot n is equal to 1. Right? Because really n is t prime hat. It's the unit vector of t prime. For this to be non-zero, that's why the path has to be nonlinear. It turns out if the path is linear, this might not be defined. I think it ends up being 0, so you can't find the unit vector of the 0 vector. All right. So if I was going to plot this, let me go back to black for the position vector here. The n is something like this, perhaps. So here's n. The unit tangent doesn't have to be the same length as the velocity, right? So this is t, but n and t are both unit vectors. Aw, man, this is why I have to talk about cross product. Rats. Well, anyway, cart before the horse. My bad. It's not my course, so haha. So t crossed into n. It's a cross product. T crossed into n gives you a third vector by the right-hand rule. It turns out that that one goes into the board, which we can use a picture like this. So, aw man, I'm sorry guys. I just realized I'm being dumb. But you'll forgive me. I may not ever be back with you again, so I get this done while I've got a chance. So the binormal is t cross n. This is a vector which is perpendicular both to n and t. All right. So let me draw a curve over here where you can see it better. Here's a curve. The tangent would look something like this, perhaps. Like this, perhaps. I'm assuming that the motion is rightward. All right. So we're talking about a path that goes like this. So here's my tangent. My tangent. The unit normal, where it points towards the direction of what's called the osculating circle. This is a circle which fits into the path locally. It just kisses the path. That's osculating is an old word for kissing. So it's the kissing circle. So like this is the osculating circle like this. All right. Here, the osculating circle over here, something like this. All right. The unit normal points to the center of that circle. So that's geometrically where n actually points. All right, like that. So once you guys learn the right-hand rule in like a day or two, maybe next class, I don't know. You take the right hand, you take your right hand, you point it in the direction of the first vector, right? Then you cross it into the direction of the second vector. So t cross n. That points my thumb into the board for the first one. And I draw this picture for into the board. On the other hand, over here, right hand, t crossed into n, it's coming out at you. So that gives us this right here for my binormal. So if I could just, for a second here, try to one more picture of what's going on. So you got t like this. Maybe you got n like this. And then you've got b like this. The thing is, you can prove that t dot n is equal to t dot b is equal to n dot b, and all of these are equal to 0. So the t, the n, and the b, they're perpendicular vectors. And they have the same geometric relation that I hat, j hat, and k hat has. They're what's called a right-handed frame. What that means is that you take the first two vectors, t and n, and you cross product them, you get the third one. So it's right-handed because they're related by the right-hand rule. I hat, j hat, k hat, same way. So one thing you could do with this t and b frame is you could set up a moving coordinate system where the coordinate system is based on using this t, n, and b relative to the particle which is moving. You could set up coordinates which are moving relative to the particle, making the particle always at the origin of that coordinate system. So you could use this to formulate something like that if you were so inclined. All right. Now, in Calculus 3, we study the change of this is called the Frenet frame. T and B is the Frenet frame. So the Frenet frame from one of the mathematicians who did this stuff early on. And let me just write down the equations. I will get back to physics very soon. It's just some mathematics. It turns out that the time derivative of the unit tangent, the time derivative of the normal vector, the time derivative of the binormal vector, they're given in terms of something called curvature and torsion. The curvature is what it sounds like. When the curve is curved, the curvature is reciprocal to the radius of the osculating circle. All right? The curvature, again, is reciprocal to the radius of the osculating circle. The torsion is a little bit more complicated, but basically if the torsion is 0, it means that the curve lies in a plane. The curve is planar. Here v is the speed, kappa is the curvature, and n, there's your n. Here you got minus speed times the curvature times the tangent plus the speed times the torsion times the binormal. And down here, minus the speed times the torsion times the normal. So every one of these, the change in the Frenet frame that you're looking at, it goes in the direction of the other ones. Like the change is always in the direction of the others. So all they can really do is change direction because they're unit vectors, right? So all they do is change directions one into another as the curve curve continues. And these equations are called the Frenet-Serre equations. They describe that time evolution of the frame. These are interesting to us because they allow us to understand what the structure is of acceleration in general. So I already derived for you up here the formula for velocity as it relates to the Frenet frame. It's very boring. Speed times the unit tangent, that's it. Where's the velocity point? It points in the tangential direction. Game over, end of story. How about acceleration? What happens there? So for acceleration, I need yet another rule of calculus here. Acceleration is dv dt, right? But it's also d dt of the speed times the unit tangent. This is a product of a function times a vector. But guess what? There is a product rule. And the product rule is simply this. dv dt